In this video, we are going to be representing patterns with algebraic expressions. So our essential questions are, what is a sequence? And how do you write an algebraic expression that represents a sequence? So we're going to be finding patterns of numbers, and we're going to use algebraic expressions to describe those patterns of numbers. So first of all, what is a sequence? A sequence is an ordered list of numbers, and each number in the sequence is called a term, and some sequences follow a predictable pattern. So we're going to be looking at basically patterns of numbers and trying to predict them and with an algebraic expression. So here I have a sequence, a very simple sequence that you might be familiar with, and it is 0, 1, 2, 3, 4, 5, 6, so on and so forth. This is an example of a sequence because it's an ordered list of numbers. It's a list of numbers that goes in order, and each number in this sequence is called a term. So this is the first term, the second term, the third term, fourth term, fifth term, sixth term, seventh term, and so on and on forever. So this is a sequence. So what we're going to be doing is we're going to be using algebraic expressions to describe the pattern that we find in a sequence. So here, let's practice a little bit predicting numbers in a sequence. So here are 4 examples of sequences, and we give you the first 4 terms. That means the first 4 numbers in the sequence. And let's try to find the next 3 terms in the sequence. So here I have a sequence of numbers that is 0, 13, 26, 39, and so on. So what is the pattern here? And let's extend that pattern the next 3 terms in this sequence. Well, it appears as though the numbers are increasing, and they're increasing by 13 each time. So if we were to extend this sequence, the next number would have to be 13 bigger, so that would be 52, then 65, 52, not sure why we're erasing all the time here, 52, 65, and 78. There we go. The next number, or the next sequence, is 4, 7, 10, 13, and so on. And if we look at the pattern here, it appears as though these are increasing by 3 each time. So if we were to extend this pattern, the next number would be 16, then 19, then 22, and so on. So that sequence continues on and on. The next one, 1.0, 1.3, 1.6, 1.9, these numbers are actually increasing by 3/10, or 0.3 each time. So the next numbers in our sequence here would be 2.2, 2.5, and 2.8, and so on, increasing by 3/10 each time. And then the last sequence, 2.5, 3.0, 3.5, 4.0, these are increasing by 1/2, or 0.5 each time. So if we were to extend this sequence, the next number would be 4.5, 5.0, and 5.5, and then that pattern would continue on and on and on. So that's what a sequence is. It's just an ordered list of numbers, and then some of the sequences we're working with here, they all follow a predictable pattern. So now we want to focus on, how do we use an algebraic expression to describe the pattern? Now I can describe it verbally, but we want to describe it mathematically. How does this sequence get its numbers? Okay, so what is the pattern here that describes how the sequence increases? So consider the following sequence: 2, 4, 6, 8, 10. So we're counting by 2s here. You can see that easily. So we want to use the fact that we know this is a predictable pattern to be able to describe it with an algebraic expression. So I've got the terms listed here. So the first term is 2, the second term is 4, the third term is 6, the fourth term is 8, the fifth term is 10, and so on. So let's try to make some predictions here. What would be the 7th term in this sequence? Well, that's easy enough to find because we already know up to the 5th term, so we could just extend this, and we know the 6th term would be 12, and then that means the 7th term would be 14. So the 7th term would be 14. That's easy to find. But now look at this next question. What would be the 50th term? Now, am I going to have to list the 8th term, the 9th term, the 10th term, and so on, all the way to the 50th term? That's going to take a while. Well, the thing we want to do is to find a predictable way to find the term, any term that we want to find, using this pattern. So if we look at the relationship here between what term we have and what the value of the term is, we might notice there's a relationship here between the term number and the value of that term. Can you see it? It's always twice as big. So the value of the term is always twice as big as the term number. So the first term would be 1 times 2. The second term is 2 times 2. The third term is 3 times 2, and so on and so forth. So the 50th term we would predict would be 50 times 2. And 50 times 2 is 100. So 100 would be the 50th term in this sequence. Now that's a much faster way to do it than having to list out every term from 1 all the way to 50 to find out. Now let's try to use that as in this next scenario. What would be the 113th term? Well, the 113th term would be 113 times 2, since it's always twice as big as the term number, and 113 times 2 is 226. So 226 would be the 113th term. And that saved us a lot of time because I certainly didn't want to list out 113 numbers to find out what the 113th term is. So here we want to generalize this. How could you find any term in this sequence? So here we found the 7th, the 50th, the 113th. What if I wanted just a general rule to find any term in this sequence? What would you tell somebody? How do you find any term in this sequence? Well, to find any term in this sequence, what we've been doing is we've been taking the term number and multiplying it by 2, right? Isn't that the rule that we would follow to find any term in the sequence? Take the term number times 2. Well, when we do that, we're going to use a variable here. We're not going to write out term number. We're going to use the letter n. N stands for the term number. So n stands for number there. The term number times 2. And now we have an algebraic expression. Take the term number times 2, and that will tell you what the value of that term is. Now, again, we want to be careful using that multiplication symbol there. So I'm going to write that as 2n. So that's how we're going to write that. 2n is an algebraic expression that would describe any term in the sequence. Take the term number times 2, and that would predict any term in that sequence. So let's try to make some more predictions. Let's take a look at this sequence: 3, 6, 9, 12, 15, so on and so forth. So what I've done is I've put them in a table where I've got the term number and its value. So the first term was 3. You can see right there. First term is 3. Second term is 6. Third term is 9. Fourth term is 12. Fifth term is 15, and so on. So what we're doing here is we are increasing by 3. Okay, this is a term sequence that increases by 3 each time. So how could we find any term in this sequence? Well, if I want to know the first term, it's 3. The second term is 2. The third term is 9. The fourth term is 12. The fifth term is 15. It appears as though I take the term number and multiply it by 3. Take the term number and multiply it by 3. And again, we're going to use n to represent the term number times 3. Or again, we want to write that as 3n. So take the term number times 3. That'll tell you the value of any term in this sequence. So what would be the 62nd term in this sequence? Well, again, I don't want to list out all 67 terms, so I'm going to use my algebraic expression here that predicts what the value of any term is and find the value of the 62nd term. So to do that, I'm going to take 3 times 62. That's the term number. And 3 times 62 is 186. So 186, if we continued this pattern on and on and on to the 62nd term, the value would be 186. So now we found the 62nd term using our algebraic expression. That makes things a lot more efficient mathematically. Let's take a look at another one. 5, 10, 15, 20, 25, so on and so forth. Here's another sequence. And the first term is 5, the second term is 10, the third term is 15, the fourth term is 20, and the fifth term is 25. How could we find any term in this sequence? Well, these are increasing by 5. So I can take the term number and multiply it by 5 to tell me the value of that term for any one of those, because 1 times 5 is 5, 2 times 5 is 10, 3 times 5 is 15, and so on. So again, that's n times 5, or 5n. That algebraic expression describes this sequence. So for any term, I just take the term number times 5, and that would tell me the value of the term in that sequence. So what would be the 37th term in this sequence? Well, I can use this algebraic expression, 5n, and take 5 times 37 to tell me what the 37th term would be. And 5 times 37 is 185. So 185 would be the 37th term in this sequence using that algebraic expression. Now we're going to bump it up a little bit. This one's a little bit more challenging. How could I find any term in this sequence? Here the first term is 6, the second term is 11, the third term is 16, the fourth term is 21, and the fifth term is 26. Well, they're increasing by 5. So I might think that maybe 5n would predict that because they're increasing by 5. Well, if I take 1 times 5, I get 5. If I take 2 times 5, I get 10. If I take 3 times 5, I get 15. And I take 4 times 5, I get 20. I take 5 times 5, I get 25. They're close, but they don't match what the value of that term is. What else could we do? Well, when multiplication alone doesn't work, we're going to have to use addition or subtraction along with that to help. So you can see that when I multiply by 5, I get a number that is always 1 less than the value of the term. So if I just added 1 to all of these numbers, I would get the right numbers. So how do I show that in my algebraic expression? 5n plus 1. 5n plus 1 would be the algebraic expression that would predict the value of any term in this sequence, because 5 times 1 is 5, plus 1 is 6. 5 times 2 is 10, plus 1 is 11. 5 times 3 is 15, plus 1 is 16. 5 times 4 is 20, plus 1 is 21. 5 times 5 is 25, plus 1 is 26. That predictably finds the value of any term in this sequence. So now I know I've got an algebraic expression that will find the value of any term in the sequence. So what would be the 80th term in this sequence? Well, I'm going to evaluate that expression for a value of 80. So n is 80. So I take 5 times 80 plus 1. 5 times 80 is 400. Plus 1 is 401. So the 80th term in this sequence would be 401. So the power of writing an algebraic expression really saves us a lot of time and gives us a lot of predictive power. Let's try one more, and this one's a little bit more challenging. Do you think you can find an algebraic expression that would predict any term in this sequence? Pause the video and see if you can find it, and then I'm going to describe what it is here in a second. So I'm looking here, and I see that this expression, or this sequence, sorry, the sequence is increasing by 3 each time, 2, 5, 8, 11, 14. So I might think it's 3 times n. But if I do 3 times n, I get 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15. So it's not getting me the right numbers, but I'm close. The numbers I'm getting are always one number too big. 3 is 1 bigger than 2, 6 is 1 bigger than 5, 9 is 1 bigger than 8. So if I just subtract 1 from all of those numbers, I would get the right values. So here is my algebraic expression, 3 times n minus 1. Again, multiplication alone did not get me the right algebraic expression, so I used addition or subtraction to adjust that to make it correct. So 3 times 1 is 3, minus 1 is 2. 3 times 2 is 6, minus 1 is 5. 3 times 3 is 9, minus 1 is 8. 3 times 4 is 12, minus 1 is 11. 3 times 5 is 15, minus 1 is 14. So that predicts it every single time that expression works. 3 times n minus 1. So what would be the 50th term in this sequence? I can use my expression 3n minus 1 to find the value of the 50th term. 3 times 50 minus 1 gives me 150 minus 1, which is 149. So the 50th term in this sequence would be 149. So a pretty actually fun activity there is writing these algebraic expressions to predict the value of any term in the sequence. So here are a couple tips for writing these algebraic expressions for sequences. If they follow a predictable pattern, then they're always going to be increasing by the same amount. So whatever the sequence is increasing by, this is what n is multiplied by. So if they're counting up by 5s, it's going to be 5n. If they're counting up by 12s, it's going to be 12n. If they're counting up by 2s, it's going to be 2n. If it's counting up by halves, it's going to be 1/2 n. And if that doesn't give you the pattern, you have to use addition or subtraction to complete the expression. You have to maybe adjust it with addition or subtraction to help you get the right values in your sequence.